Welcome to the narrated PowerPoint video for Lecture 26 for BBE 4023, Process Control and Instrumentation. This presentation is about process stability. For this presentation, we will review the definition of process stability that was originally given in Section 14, where a process was said to be stable if the process outputs and all intermediate values and signals remain within an acceptable range. Another way that process stability is defined is as a process that has bounded outputs if it is given bounded inputs. But that leaves us with the question, what are the bounds? We will talk about output bounds in terms of saturation. Then I will go over some examples showing how to use the Routh stability criterion to assess process stability. Finally, you should begin to think about what you might do if you find that a process is unstable. How do you take an unstable process and make it stable? One key thing about making a process stable is to make sure that every part of the process stays within the physical limits of the equipment. You cannot claim that a process is stable if occasionally tanks overflow in a process involving liquid levels, or a process is not stable if the controller for your water heater calls for 10 kilowatts of power, but the circuit and the relay used can only supply 5 kilowatts of power. If any internal process elements or the process output exceed desired bounded outputs, the process is not considered stable. Other process stability indicators are the limits on sensors used. Your process will not be stable if the process that is measured is 200 kilopascals, but the sensor that you're using only goes to 150 kilopascals. Do you remember in lab when you were using these single-turn potentiometers and we had you set the chart recorder scale incorrectly? The recorder showed a flat line, but the actual reading was something off the scale. It would be hard to maintain stable control if your controller cannot see the correct measured input. Internal signal conditioning equipment has range limits too. Think about the PDAC 55 unit we talked about at the beginning of the class. It has filters and amplifiers that condition the analog signal coming through the analog inputs you have connected to the PDAC 55 unit. If that analog input is too large, you will saturate the filters and amplifiers. When electronic components are saturated, they cannot do their job correctly, and the readings that the controller gets will be wrong. You can also run into limits with actuators. Again, if your process controller tries to get a valve to open to allow 5 kilograms of material to flow, but the valve cannot handle more than 1 kilogram per second, your process will have stability problems. So if you're working with a process that is not performing as expected, check on the limits of the different pieces of equipment. In process control, the term saturation describes the condition when any device hits a physical limit. The overflowing water bottle is saturated. It cannot hold any more water. An amplifier that cannot amplify the input signal as expected may be saturated. A valve that cannot allow the fluid flow that is called for may be saturated. Saturation should be avoided because the process response will be limited. Electronic equipment should not be saturated either. Devices that have been saturated usually will experience some delay in their response. So if you have a saturated amplifier, it will take some time before the amplifier will respond properly after the input signal drops below the saturation limit. On-off devices like relays can operate near their limits. The relay shown can handle loads up to 25 amps and 240 volts AC. That is equal to 6,000 watts or 6 kilowatts. You should be able to use this relay to handle a load near 6 kilowatts without difficulty. So for a process to operate properly and to be stable, it is important that none of the equipment is saturated. Processes can become extremely unstable if parts become saturated. The rest of this presentation is about the Routh stability criterion. This analysis can be done very early while a new process is being designed. It can be done before the equipment is purchased to make sure that the equipment purchased has the performance criteria needed to produce a stable process. The Routh stability criterion begins with the overall transfer function for the process. This is the same type of transfer function we've talked about for a long period of time. The process output C over the input function R is given by the ratio of two polynomials with constants and different powers of S. For this analysis to work correctly, the numerator power needs to be less than or equal to the denominator power. So you either need to be given the overall transfer function, or you need to find the overall transfer function given the block diagram with the transfer functions for each process element. For the Routh stability criterion to work, the denominator of the transfer function expression needs to be written as a polynomial set equal to 0. When the denominator is written as a polynomial and set equal to 0, it is called the characteristic equation. We need the values of the coefficients a0, a1, a2, and on. The results of the Routh stability criterion analysis only indicate if the process is stable. The results do not tell us if the process is sluggish or oscillates. Let's go through some examples. Here is example 1 from the course packet. We are given this block diagram and the element transfer functions. We are using proportional control with a gain of Kp. The process is a second-order process. We do not know physically what the process is, but we have the transfer function shown. Our feedback element has a first-order response as shown. The first step is to find the overall transfer function shown here. The second step is to write the denominator as a polynomial. To do this, we multiply the numerator and denominator by 1 in this form to eliminate the fractions in both the numerator and the denominator. Now we set the denominator equal to 0. This expression is called the characteristic equation. Then we need to multiply the terms out to put the expression in the form of a polynomial. Now we need to find the coefficients a0, a1, a2, and a3. We are given tau 1 equals 1, tau 2 equals 1/2, and tau m equals 1/3. Kp, the proportional gain constant, is a variable. It is okay to have one variable. After plugging in the numbers, we get the values for a0, a1, and a2. a3 is equal to 1 plus Kp. Now we can do the first check for stability. Using the Routh stability criterion, all of the a values must be greater than 0. So now we can check that all the coefficients of the characteristic equation are greater than 0. In this case, they are all positive because Kp will always be a positive value. If a0 is negative, you can multiply the characteristic equation by -1 to change the sign. Then you can apply the previous test. Again, after multiplying by -1, all the coefficients must be greater than 0. So essentially, for that to be true, all of the original coefficients must be negative. Now that we've passed the first Routh stability criterion, we need to create the Routh array using the coefficients from our characteristic equation. The coefficients are shown in the upper right corner of this slide. Now look at the array table. The first column labels the rows. The first row has the even-numbered a coefficients from the characteristic equation, so it lists a0, a2, a4, and on and on. The second row has the odd-numbered coefficients from the characteristic equation, so it lists a1, a3, a5, and on as needed. The next row will be calculated coefficients labeled as b's. The next row will be calculated coefficients labeled as c's. This slide shows the Routh array with the first two rows filled in. Now I don't know about you, but fractions are just more difficult to handle. One nice thing about the Routh stability process is that you can multiply the coefficients in any row by a constant to get rid of fractions. So we're going to multiply the coefficients in the even a row by 6. Here is the Routh array after multiplying the first row by 6. The next step is to calculate the b's and c's. Here are the equations for calculating the b terms. They use the a terms. You can find the equations on page 25-3 of the course packet. After plugging in the numbers, we find that b1 is equal to 10 minus Kp, b2 is equal to 0, and b3 equals 0. Here is the array with the b coefficients in the Routh array. Next we need to find the c values. Here are the equations for calculating the c terms. They use the odd a and the b terms. You can find the equations on page 25-3 of the course packet. After plugging in the numbers, we find that c1 is equal to 1 plus Kp, c2 is equal to 0, and c3 equals 0. Here is the array after filling in the c and d values. We can stop when we get a 0 in the first column of numbers. Now we can apply the Routh stability test. We look at the first column of values. Those are the values of a0, a1, b1, c1, and on until we get to a 0 value. For a process to be stable using the Routh stability criterion and the overall transfer function, The values in the first column of values must be positive and non-zero, excluding the last row and the subsequent rows, which will be 0. For the Rouse stability test to be true for this case, where we have a variable kp, we need to look at the terms with kp in them. Remember that the values in the first column must be positive. A0 is 1 and A1 is 1. They're both positive. For B1 to be positive, kp must be less than 10, and for C1 to be positive, kp must be greater than -1. So this process will be stable as long as kp is between -1 and 10. In reality, kp will be greater than 0, so this process will be stable as long as kp is between 0 and 10. This slide summarizes the steps for using the Rouse stability criterion. Write the overall transfer function. Write the characteristic equation as a polynomial. If A0 is negative, multiply through by -1. Check that all A's are positive. If any are negative, the process is unstable and you are done. Complete the Routh array, fill in the A coefficient, and calculate B's, C's, and D's as needed. Check terms in the first column. They all must be non-zero and positive for a stable process. Keep variables in the Routh array. Here is another example that is in the course packet. In this case, we are given the characteristic equation, so our first step is to check if all the coefficients are positive. They all are. Here is the Routh array with the A values inserted into the table. The coefficients are listed in the upper right corner. First, we need to find the B values. We have a fraction, so we multiply by 3 to get rid of the fraction. Then we need to find the C values. Again, we have a fraction, so we multiply by 11. Then we need to find the D values. All the values in the first column are positive, so the process is stable. Here is example 3 from the course packet. It is the same process as example 1, except that we now will use PI control. We are given the values for the time constants and Kp and tau I. Here is the overall transfer function. Here is the characteristic equation set equal to 0. After reorganizing and multiplying it out, we get the polynomial form we need. At the bottom of the slide is the equation using the variables. After substituting in all the given values, we get the values for the polynomial coefficients listed in the column. We have fractions. To avoid using fractions, we multiply by 24 to get the coefficients in the right column. If we apply the first test, all of the coefficients are positive, so we go and complete the Routh array. Here is the completed Routh array with the characteristic equation coefficients in the first 2 rows and the B's and C's calculated. Once we get a negative value in the first column, we can stop. The negative C1 value means that this process is not stable. This is a good time to ask, what can you do if you find out that a process is not stable? Well, we need to change the process. But what can you change? Let's go and look at the process. What can be changed and how? Well, you can change the type of control. Example 1, which was the same process using Kp control, was stable as long as Kp was between 0 and 10. What else can we change? You could change the values of Kpi and tau I. We were given the values of 5 and 0.25. Maybe with the right values the process would be stable. The next video will cover tuning controllers and finding values of Kp, tau I, and tau D. This is the most likely thing that will be done to make the process stable. Find better values for Kp and tau I. You might also be able to change the process so that other time constants will change. This block diagram does not tell us what the process is or what the tau values are based on, but you might know the original process and be able to change the time constants tau 1, tau 2, or tau m. This might be much harder if the process exists, but it might be something to keep in mind. Another thing that you might do to make the process more stable is to add cascade control or feed-forward control. So you have options, and it is up to your creativity to find the best one to create a stable process. This slide summarizes the key points covered in this video. One key thing to note is that there are additional ways to analyze processes. They are not covered in this class because we do not have enough time. If you get into process control, you will want to learn about these other analysis methods. This is the end of the Lecture 26 video on process stability and the Rouse stability criterion. Write down any questions you might have and bring them up in class.